Good morning everyone. Myself Dr. Shashikant Goilkar, Professor Mechanical Engineering Department, Finolex Academy of Management and Technology, Ratnagiri. Here at this point of time we are going to discuss about the damped free vibrations. In earlier topics we have discussed about the equation of motion in simple single linear spring mass system as well as torsional vibratory system. Here the equation of motion of single degree of freedom damped free vibration system gets slightly changed. One additional term in the which is known as damping term, damping force, comes into picture. If we see the schematic of any single degree of freedom vibratory system, we have in such case one spring element, one damper element and one mass, and it has a motion as shown in this figure. So this has amplitude of vibration as well as velocity as well as acceleration of the mass with respect to its reference level. So in this case, if we consider single degree of freedom damped free vibration system, vibratory system, we get additional term as Cx dot, which is the damping force. And one important thing to remember in such case is that here this system consists of three forces, and the summation of these three forces are in the system comes into the equilibrium, maintains its equilibrium after the summation of these three forces. And these three forces are like inertia force, damping force and spring force. And since the excitation force in such case is not present, since we are considering the system as free vibratory system, so excitation force in such case is considered as zero. So together this equation of motion becomes inertia force plus damping force plus spring force is equal to 0. And characteristic equation of such can be developed further in this way, and in such case we get roots of the equation, solution to this equation with three conditions. These conditions are highlighted here, like over damped system, critically damped system and under damped system, and the response of corresponding systems are given in the form of equation as shown here. Now there are in every vibratory system generally, or we can say in general that every vibratory system which is having viscous damping into it gets categorized in the form of over damped, critically damped or under damped system. So the response of this system after relieving this mass from a particular position depends upon the parameters involved into the system, and based on that the system respond to the initial excitation. In this case every system, every over damped, critical damped and under damped system has its own importance. Out of these three, the most what we can say, the most of the time we observe the systems in the form of underdamped systems, and critically damped system has its own advantages. We can, for example, we can take as the gun firing system. So we have the theoretical mathematical treatment and all these things can be discussed later on. However, just here I want to highlight that in case of the viscous damping system, single degree of freedom damped free viscous damping system, there are generally three types based on the after solving this equation of motion with the help of its characteristic equation, we get three types generally, that is over damped, critically damped and under damped. And in those cases, as we have seen that when the c square minus 4 km is greater than 0, the system is over damped. When it is equal to 0, the system is critically damped, and less than 0, system is under damped. And the response of such systems becomes like this: when the damping ratio is more than 1, the system is over damped. When it is equal to 1, it is critically damped, and when it is less than 1, it is under damped. And in most of the cases, the interesting damping condition is the under damped system, in which the vibration amplitude or displacement goes on decreasing with respect to time, as shown in this figure. There is further mathematical treatment related to this under damped free vibratory system that we can cover in the next sessions. The mathematical equations related to the under damped free vibratory system. Thank you.